a quick test of the audio to see if anything's coming out. Well, hello everybody. Hope you've had a lovely bank holiday VE day today, and the weather's been good to you, has been here. So, and thank you for turning up for this live YouTube session. It's a shame we couldn't hold it in person, but it's better than nothing, I suppose. Keeps some sort of normality around. So tonight's talk is all about things that go bang in the night, and in particular, mostly about supernovas and things like that. So let's get started and see what we can find out. Hoping that the sound is all coming through okay and everybody can hear. There is a bit of a thing with these presentations is that YouTube, by the time it gets through to you, it's about 30 seconds after I've said it. So when I glance across to look at the comments, sometimes they're a little out of sync. Anyway, I hope this is all coming through. So let's consider what makes the biggest bang in the universe and what is the most interesting to see. So that's a topic that we're going to cover tonight. And I put this slide in once I'd written this talk, which was about 2 years ago, and it still seems relevant even today that this is quite a possibility that this could be the biggest bang that we will experience. But before I get into space-based things, I'd really like to tell this little story about something that's slightly space-related, but has actually happened on Earth, and was one of the first things to enter orbit way before the space race really got started. And this is 1956, and was Operation Plum Bob. And this was part of the nuclear weapons testing that the United States underwent. And one of the things they did was to drill big holes into the ground and put nuclear weapons in there and detonate them to get data on them and to find out how they were working. Well, one of them, this Operation Plum Bob, run by Dr. Robert Brownlee, he was in charge of this one, and the Pascal A one, they did exactly that. They dug a big hole and they put a nuclear weapon at the bottom of it and triggered it, and they got what they described as one of the best Roman candle displays that has ever been seen. Something like this that shot up out of the ground. So that was very effective. Then they went to, but they decided that there was quite a bit of stray debris that was created by this, so they decided to do the Plum Bob B, Pascal B version, by welding a large metal plate across the top and detonating it with that and trying to enclose somewhat the experiment. So they put this large concrete and metal cap that weighed at least half a ton across this 400-foot deep borehole after the bomb was installed in it, and welded it shut to steal all the equipment in. And then did a few calculations at that point just to see whether they thought this would hold or not. And there was some confusion about this, so they decided to set up a very high-speed camera just to film the lid of this, just in case their calculations were wrong. Anyway, it was duly detonated, and reviewing firstly, there was no sign whatsoever of this end cap of this nuclear explosive tube. And reviewing the footage of this very high-speed camera, they found only one frame with the cap in it. So it obviously shot off at an enormous rate of knots. And although they had no idea exactly how fast it was going, based on how quickly this was being observed by the camera, this one frame, they had a lower limit, and they worked out it was moving at least 60 kilometers per second. So that's pretty fast, especially when you consider it's about 11.2 kilometers a second for the Earth and 42 kilometers a second escape velocity for the Sun. So this thing going at 60 kilometers a second was probably the first thing to enter outer space, and possibly even to leave the solar system, because it was given in mighty punch to get it going. So that was possibly the first thing that went into orbit, this large metal sort of drain cover that went shooting off into space. So I just thought that was interesting. That was one of the biggest bangs on Earth anyway, but related in some space-based things. So now to get on to the topic in more detail. Firstly, we've got to cover some star theory. There's quite a bit of theory needs to go into this talk so that you can understand it. I've tried to make it as painless as possible, so I hope that works. But let's see. So this is how a star works. So you have this big mass of hydrogen and helium, basically this yellow blob, and there is an enormous amount of gravity with it. It's 3 times 10 to the 30 kilograms, 2 times 10 to the 30 kilograms, sorry, mass in the star, many times the mass of the Earth, all trying to squash it down to absolutely nothing. So this huge mass of gravity, all trying to compress it down to nothing. But countering that, you have inside, where it's got very, very hot due to this compression, you have the nuclear fires burning, and they are trying to throw things as far away as possible. They're exerting an equal pressure outwards, and eventually they come to some arrangement where the gravity exactly balances the nuclear power, pushing the star apart. So they settle into what's called hydrostatic equilibrium, and they sit there and they just sort of evolve there, and it's really quite stable. If the star gets any bigger, for instance, if it starts to swell up, then it basically loses some of its fusion properties, cools down, and it starts to shrink again. And likewise, if it goes in the other direction, it tends to heat up, and then you get more fusion and it gets bigger again. So it kind of settles down into quite a nice situation where it can settle down. Question comes though when you run out of fuel. So you run out of this power in the center, and then you've suddenly no longer got a force pushing outwards on the material, and you've got a big contraction inwards. And that's kind of what powers a lot of these phenomena we're going to talk about tonight. So once you run out of fuel, you run out of this balance and everything goes wrong. Now for a sun, when that happens, we'll end up as a white dwarf because we don't really have the power. Even though we have a lot of weight in the sun, we don't have enough to do anything exotic. So it just collapses down until it gets to quite a stable state called a white dwarf. And we probably all know of the one around Sirius. So this is Sirius B, this one, the white dwarf, that orbits Sirius A, the dog star. So that's a white dwarf. That's the end state of our sun, and not very interesting. It's sort of a stellar cinder, just sits there doing nothing. And they live here in this part of the Hertzsprung-Russell diagram. You can see they're not very luminous. If you can see the cursor, this is not very luminous down here. One is the brightness of the sun. So these things are brighter than the sun, and these things are, less bright than the sun. And this is the temperature. So here's the sun on this. We're a G star. White dwarfs are often much hotter than the sun because they've collapsed down and they've gained all this energy by collapsing down. So that's a white dwarf, and they're usually fairly dead, don't do very much unless something else happens to them. And this is what can happen in some types of nova. You can get all sorts of novas, but these are the sort of catastrophic novas. And here we have a white dwarf on the left with hydrogen and helium just sitting there doing nothing. It's certainly not burning anymore, it's just glowing hot. But it has a companion, which could be a red giant or a red dwarf or something that can be very close in orbit around it. And it can, certainly towards the end of its days, it can start to puff up, and some of the loose material on the outside of the still burning star can bridge across onto the white dwarf. And this one here starts to steal the material and make a sort of a duvet blanket of material. This is hydrogen that's being stolen from this star. And not only is it being stolen and making this bigger, but it's actually falling onto the white dwarf at quite a rate because they are very compact objects, as we'll see shortly. So as you drop onto them, you drop on with quite a force as you get nearer and nearer to it. And so these tend to heat up, and this blanket gets hotter and hotter, and at some point you get a thermonuclear explosion of sorts that burns through this outer layer, and you get a big shedding of extra material shooting off there as this thing burns, blows off its outer layers and brightens considerably into a nova. And then, after a little while, it settles down again, and we get back to where we were. So here's GK Persei. This is one of these recurrent novas, and they can go through this process several times. So you can imagine they steal some material, it all gets a bit too hot, they trigger this nuclear burning, we get a big explosion, but it doesn't destroy the star in this case. It just kicks off the outer layers, settles down again, and then gets back to stealing material. So now a few more definitions, just to so you'll understand some of the later bits of the talk. So I've talked about white dwarfs. So this is the end state of a star like our sun, because it's just not big enough to do anything else. These weigh less than 1.5 times the sun. If they're bigger than that, then they will no longer be a white dwarf. And so they're 1.5 times the mass of the sun at maximum, and they're about the same size as the Earth. So you can see after they've done all their burning and collapsed down, they collapse down to something very, very small, something about the size of the Earth. So I say not very big, but very hot. All that energy of collapse has to go somewhere. The next biggest thing up is a neutron star. These are much smaller, so this diagram is not to scale. So these are somewhere between the biggest white dwarf at 1.5 solar masses to somewhere between 3 and 5 solar masses. We're not really sure exactly where this boundary is. So that's still work in progress. And these are much smaller, 20 kilometers across, so the size of a big city, something like that. Very difficult to detect unless they indicate themselves to you in some way, which luckily a lot of them do as pulsars. So that's the next big end state of a star, if it's of this particular size. Above that, we don't know of anything that will stop it collapsing down, so it will turn into a black hole at that point. So certainly above 5 solar masses, if what remains of a star is above 5 solar masses, you're going to end up with a black hole of some sort. And we've no idea how big they are, because you can't see inside a black hole. But the event horizon of something like this is probably somewhere of the order of 30 kilometers. So perhaps a little bit bigger than a neutron star, but then this isn't actually the physical size of the black hole. This is just the point of no return, the event horizon. If you go past the event horizon, there is no way back. Now, if we look at the state of matter in each of these, this is quite interesting. So regular matter looks like this. You can see my cursor here. So this grey bit is the nucleus, so that's sitting at the centre of an atom, and this is the electron going around it, this green dot. This is not at all to scale. Atoms are nearly all empty space. The nucleus of the atom, if you sort of blew it up to something that you could handle, such as a marble. So if you took a marble to be the same size as the nucleus of an atom and put that on the centre spot of a football pitch, the electron would be going around the stands of the football pitch. So you can see most of it, all the football pitch would be empty matter in an atom. And the density inside a star like the Sun is about 0.1 kilograms per cubic centimetre, and a cubic centimetre being about the size of a sugar lump. So about 100 grams per cubic centimetre is the sort of density you get inside a star like the Sun when it's actually active and burning. Now, when you get to a white dwarf, you've got a different state of matter. A white dwarf has been crushed down to squashed as closely as the atoms can get. And at this state, you get some very funny effects. And this is called degenerate matter. And you can see there, you've got 10,000 kilograms per cubic centimetre. So that's a very heavy sugar cube, that is. And in this case, the atoms are packed almost as tightly as they could possibly be. In fact, there is no room to sort of pack any more atoms in at this point. So this is why you get these huge densities. And they're stopped from compressing down any further by some quantum mechanical effects called, well, it comes called degeneracy, but it's basically fermions that stop it. So you can think of these as that there is a state in every place for an atom to be in. And it's a bit like all these pigeonholes. There is a pigeonhole for every atom to fit in. Usually, in regular matter like we have around us, lots and lots of these pigeonholes are empty, and you've got lots of places you can put these atoms into. So they could just be scattered sort of anywhere around. But when you get down to degenerate matter, you're basically filling up all these pigeonholes until you've run out of places to put them. So this is kind of what is stopping the star from shrinking anymore, is that you haven't really got anywhere else to put these atoms in. It's a quite a poor analogy in some ways, but it's probably the best one I could come up with. So we've got all these places that quantum mechanics say you can put an atom, and we've filled them all up, and that's what's stopping the star from squashing down any smaller. So this is called degeneracy pressure, and it's the electrons really that are stopping you going down any further. So it's called electron degeneracy pressure. So that's what stops a white dwarf collapsing any further. But this is only good up to a certain level. Above a certain level, the electrons can no longer withstand the pressure. And that's when you get into these neutron star material. And this is a staggering amount. This is 10 to the 14 kilograms. So I think that's Mount Everest per sugar cube. It's that sort of weight. It's a huge thing. So in this case, all the electrons have been squashed right into the marble. So it's the atom is no longer taking up a football stadium. It's just taking up the size of a marble. So you can see there, you can squash them much closer together. And it's the same sort of effect as electron degeneracy pressure. But in this case, it's the neutrons in the pigeonholes. There are only so many pigeonholes you can put neutrons in. And this is what's providing the pressure. You've filled up all these holes with neutrons, and there's nowhere else to put them. But again, this is only good up to a certain state. And eventually, even this will be overcome. And this is where we get into a black hole. That there is nothing else that will withstand the gravitational pressure. So that's a bit of the theory about why things get to that state. And now just one quick other term, at least. This is an FOE, and you'll see this at the top of some of the slides. So this is a unit of supernova power. So it stands for 10 to the 51 ergs, or 10 to the power 51 ergs. I don't know quite why we still use ergs in some branches of astronomy, but they still seem to be around. Joules is the more modern use. That's 10 to the 44 joules. Both are pretty meaningless in terms of real everyday life. A 1 joule is about the energy you expend lifting an apple from the ground up to your mouth. So not a huge amount. So 1 FOE is about the energy you'd get from totally destroying 186 Earths. So that's quite a lot of power. And this is the sort of unit that we use to measure supernova in. But I'm not going to start with supernova. I'm going to start with a close ally of them, which is the kilonova. Now, kilonova is what happens when you get two neutron stars, two of these very, very dense things, orbiting each other and eventually running into each other. So this is a neutron star merger. And they're going to release about 10 FOEs, as it says up there, 10 to the 45 joules. So this is quite a explosive event. I hope this video comes out okay. This is a NASA video, I think, showing what happens as two neutron stars merge. At this point, they're getting very close and giving off a lot of energy in gravitational waves, which lets them get closer and closer. And then they finally merge, and there's a big explosion. And as you might imagine from two neutron stars merging, there's a lot of neutrons around, and these are particularly easy to make a lot of sort of the heavy elements from. So neutron star mergers is where we think quite a lot of the heavy elements like gold, platinum, things like that come from. And this is one of those neutron star mergers. We helped a lot detecting these with the coming online of the LIGO gravitational wave detector. So this is a brilliant machine used to detect gravitational waves, and it picked up one of these neutron star mergers. It's GRB one here, and this is one that we could actually detect and point telescopes at. So it was detected by 3 of the gravitational wave detectors, 2 LIGO ones at Hanford and Livingston, and one in, I think it's Germany, Virgo. So that was another detection. With 3 of them, people were able to pinpoint on the sky about where it was, and astronomers could follow it up. And they did indeed follow it up and found an optical light source of it there. So this is the 2017 event, and this led to one of the most authored papers in the history of astronomy, with several thousand astronomers on the author list, of which I am not one of. I am one of the few who's not on this paper, because I wasn't near a telescope at the time. So anybody who was anyone near a telescope basically got on this paper. And this was the follow-up. And they think it probably produced 200 Earths worth of gold and 500 Earth worths of platinum. So well worth going off there prospecting, if only it wasn't about 1 billion light years away. But a very powerful event, and one of the more extreme things that is occurring in galaxies. Happens over just a few milliseconds, so a very quick event. But now on to supernova, which is what most of this talk is about, because they're kind of the most exciting of the big bangs that go off. And they're some of the quickest events going around in astronomy. Nearly all the things that we study in astronomy take place over millions and billions of years, so it's really nice occasionally to have something that's really quick. So let's start with a few historic supernovas and see what we know of in the past. So these are some of the more notable supernovas. Supernovas are named, as you can see there, as SN for supernova and the year of their happening, and then a letter after that if there's more than one. So for the ancient ones, there isn't, because they had to be quite bright to be able to see at all. So supernova 10,006 was widely reported and was the brightest seen at a magnitude of -7.5. That is really pretty bright, as anybody, I'm sure you understand. Venus is what, about -3, and it's logarithmic scale, so that's several thousand times, or at least 1,000 times brighter than Venus at its brightest. So that was widely reported in ancient texts, and we've been able to find it since. Then supernova 1054 would be the one that created the Crab Nebula. And then we don't really have anything until 1572, and we have 2 in quick succession there. Tycho's supernova in 1572 at about -4, and Kepler's in 1604 at -3. Then there was one in 1680, but nobody really saw it. This is only one we've noticed since then, because it was magnitude of 5, so only just in the visible perception, really. CADAS, highly obscured in dust clouds. And then the nearest one we haven't had one in our galaxy in recent times. So 1987A is the most recent one that's been anywhere close, and that was in the Large Magellanic Cloud. And at +2.9, it wasn't particularly stunning. It was easily noticeable by telescopes and even amateur astronomers and anybody who knew the night sky and was in the southern hemisphere. But it's not particularly stand out as some of the others go. So just a few of the pictures. So this is 10,006 as we see it now, and it's a type 1A. I'll go into the various types very shortly, but just to give you a head up. So that's the type 1A, and that's what we see of it now. So it's reasonably easy to sort of roll the clock back on these and say, well, this is how much it's expanded since its created, and you can actually measure how quickly that shell of material is expanding. So you can roll it back and work out when it went off. So this was the result of the 10,006, and we know roughly in what part of the sky it was anyway from reports. Then, of course, the Crab Nebula, 1054. I'm sure a lot of people have seen this. This is M1, the first entry in Messier's catalogue, and this was a Type 2 supernova. Went off in 1054, and we can still see the cloud expanding. And in fact, we've got enough data to actually see the internals. This is the very internals of that one. This is the pulsar right at the very center of the Crab Nebula, what's left of the star after the supernova. So you can see there it's pulsating away. This is Tycho's supernova in 1572. This was also a Type 1a, which I say I'm going to come back and explain the difference between those. And then Kepler's supernova. We have two in quick succession at that point, and that was also a Type 1a. Now, just to go and cover the taxonomy of supernovas, what they're called. So this is the taxonomy that Rudolf Minkowski and Fritz Zwicky came up with. So they say basically, if you find a supernova, then you go and take a spectrum of it. And if you see hydrogen lines in it, then it's a Type 2. So you go down this branch. If you don't see any hydrogen lines, then you go down this branch and it's a Type 1. So those are the two broad categories. Does it have hydrogen in its spectrum or not? And that distinguishes Type 1 from Type 2. But they reasonably quickly found that there were subtypes of Type 1. So this is where we have the Type 1a. And if the spectrum contains silicon lines in it, so there's a good deal of silicon in the spectrum of it, then it's Type 1a. If it contains helium in the spectrum, it's Type 1b, and if there's no helium, it's Type 1c. So this is their categorization system that they came up with. And they actually did have some more. They had a Type 3, a Type 4, and a Type 5, but those are no longer considered. They've all just sort of subtypes of Type 1 and Type 2. The only problem with this is that it's not a particularly good scheme now that we know a little more about what's going on. So the difference really is that there are two types of mechanism. There's the Type 1a, where you have a star that detonates, so it explodes. And then you have the Type 1b, the Type 1c, and the Type 2, and these are all sorts of core collapse supernova. So this is a little like what I said right at the beginning. This is where you switch off the power of the star and it all collapses onto the core. So the core switches off and everything comes collapsing in, whereas the Type 1a is a detonation where the star just basically burns and explodes. So often the distinguishes is a little loose, sometimes even with professionals, that they talk of Type 1s, which are, and they really mean detonations, and Type 2s, which mean core collapse. But you just have to remember Type 1b and Type 1c are also core collapse. So let's go and take the sort of easy one first, the Type 1a detonation. And this is really just a nova on steroids. And typically 1 FOE to 10 FOE, something like that, is the type of radiated power from this. And again, this is a white dwarf stealing material and building up this jacket of stuff. But in this case, it's building up a large amount of stuff, and it's also very, very close to this limit that a white dwarf can get to. If you remember, I said 1.5 solar masses, so once you get to that, you're in danger of collapsing into a neutron star. And it used to be thought that was probably what triggered this, that it got to this boundary and fell over and collapsed into a neutron star and detonated in that way. The more recent thinking is that it's actually shocks and sort of trauma that accompany getting to this stage, and just before it gets to this stage, it actually triggers. So it builds up this jacket of stuff, just like in a nova, gets very, very hot until it starts to burn. And I said that white dwarf is made of this degenerate matter, which has very strange properties. It's not like regular matter. When you've squashed stuff down to such a condensed environment, firstly, it burns in a very odd way. It doesn't expand. Nearly everything you set fire to, dynamite, gunpowder, petrol, anything like that, expands as it gets hotter. But white dwarf degenerate matter doesn't, or only very, very, very weakly. So once you set fire to it, it doesn't get any bigger. It just sort of burns and sits there at about the same size. The other strange thing about degenerate matter also is if you add extra mass to it, so as this stuff is falling onto the white dwarf, it doesn't get bigger, it actually gets smaller. The white dwarf contracts as you add more stuff to it. So as I said, degenerate matter is very strange stuff. But when it does start to burn, you start to get this nuclear flame, and it doesn't kind of release, it doesn't get any way to release the energy. It doesn't sort of explode out. It just sits there as a very hot burning thing, and it just burns all the way across the star. This wave of burning just moves across the whole star from one side to the other, and just gets hotter and hotter and hotter until eventually, I said it does respond very, very weakly to temperature. Eventually it gets really, really hot, up to millions of billions of degrees Kelvin, and then it finally does sort of detonate and explode. But it takes a long while to get to there. And this is that was my poor animation of it, and this is a much better animation by somebody at NASA who clearly had a bigger budget than I did. And you can see they're stealing stuff and then exploding, except pretty sure in most of the cases you don't get any remnant left behind, it just detonates. And this is quite a nice model of it done by, I forget who, but I think it says at the end. So this is the burning starting at the very center. In this case it's asymmetric burning, and you can see there it's just burning all the way out. But the star isn't really growing any particular size. This wave of burning, just burning, setting light to the whole of this white dwarf, getting hotter and hotter until eventually it does detonate. But it's not a particularly eruptive thing until it gets extremely hot, and then it does erupt out. And here we have a Type 1a supernova 2011 FE. So I think these are named very much like you name asteroids, and actually quite a lot of things in astronomy. So supernova SN 2011 is the year. Then the next letter is sort of A for the first half of January, B for the second half, C for the first half of February, etc. And then you tack another letter on for, so it'd be A for the first one in January, B for the second one in the first half of January, and so on. So you can see there we're getting through quite a few in 2011, and these days we're getting hundreds a month detected. Type 1As are very popular with astronomers because they always seem to detonate at this particular boundary of about 1.5 solar masses. So we know about how much light they give off, and we can use that to map the universe. There is another odd type of Type 1A called a 1AX, which is less powerful. It's very rich in helium, and although they're quite common, they're not as bright, but that's just a sort of by the by. And this is what a supernova generally looks like. This is the light curve, so this is time along the bottom, time along this axis, the number of days. This is brightness up here. So you can see it actually detonates over here somewhere, and you don't really see any of the detonation. It's only later on that it gets brighter and brighter over a few days, brightening to its peak. And this is caused by short-lived radioactive isotopes. So in this case, it's nickel-56 that is giving this brightness here, and then cobalt-56, slightly longer-lived isotope there. And you can see in this sort of animation on the left, you can see the supernova actually brightening, getting brighter there, and you can see on the right the light curve of that as it gets brighter over a few days and then dims down. So that's the typical signature of a type 1a supernova. And although we like to think they all go off with about the same size and intensity, they don't really. So this is several supernova 1As all plotted on the same graph, all to the same scale, and you can see there's quite a variation of them. They all follow roughly the same curve, but not exactly the same curve. However, it's been found that if you look at the width of the curve, that allows you to recalibrate them. So you can then sort of put them, recalibrate based on how wide this light curve is, and then they do all more or less fall on top of each other, and we get a lot better scale for mapping the universe. Quick note about the type 1b and type 1c and type 2 core collapse. So they're all caused by the same thing. The star will burn, and this is what happens in our sun, that it burns hydrogen to helium, and then you get a big residue of helium in the middle. And with our sun, it's just about big enough then to burn in its very late stages some of that helium to carbon. But beyond that, it runs out of power and then just collapses down to a white dwarf. It does nothing more exciting than that. But with a bigger star, you can actually start to burn some of these other elements. So you can go on to burn oxygen up to magnesium, and similarly up to silicon, and even to iron and things like that. But eventually you run out of power, and then your sort of engine in the center switches off. So this is what happens in a really big star. You have all sorts of things burning at the same time. You have iron in the center, which won't burn, but then silicon, oxygen, neon, carbon, helium, and hydrogen all burning in different shells, and it's called onion burning. No relation, I have to say, but that's what happens in a really big star. It can be burning lots of elements at the same time, but it's a bit of a losing battle, because the amount of energy you get from burning silicon is tiny compared to what you get from burning hydrogen. So it's a law of diminishing returns, basically. And this is roughly what happens. So something happens in the core, and the core disappears. It's no longer burning, giving outward pressure, so it collapses in. This is followed up very quickly by the outer layers also collapsing in, no longer held up. But then there's some sort of bounce that happens, and we're not 100% sure exactly what causes this bounce, but the outer shell collapses in, it pauses and stagnates for a while, and then it bounces outward and explodes outward. So that's what we're seeing here. It's exploding outwards, and this is another animation I did to sort of put that together in a bit quicker way, so you can see it there collapses. Then we get to this stall stage where we're not quite sure what happens, but there's this white ring which is a whole load of neutrinos that are given off by the very center, and they push outwards, and we think that may be what causes the sort of bounce. So here it is again. Neutrinos hardly ever interact with material, so they're a very poor thing for being able to push out, were it not for the fact that 99% of the energy of a supernova comes out in neutrinos. So there is a staggering amount of neutrinos. So even though they hardly ever interact, there's just so many of them, we think that's probably what unblocks the stall and causes the star to explode. There it is for the final time. And this is supernova 1987A in the Large Magellanic Cloud. We can see there a ring of material that's been blown out from the supernova. So we do know they do explode and send out this ring of material, despite our best models of them not always behaving. And you can see, oops, missed that, sorry, go back. Go back and do that again. So this is lots of pictures taken over time of this 1987A, and you can see this ring of material brightening over the years. And this is not actually the ring of material moving outwards. That ring was already there. It's actually the light and particles coming out of the supernova that have reached this previously ejected material and now brightening it up. So that's what we see there. Just to sort of cross all the T's and dot all the I's, this is a type 1b, which is the one where we don't see any hydrogen in it. I think what happens here is the star burns quite fiercely and it loses all its hydrogen in the outer layers. These are blown away in the course of its burning, and then when it comes to the core collapse, there's really only helium left to collapse and a whole load of other elements. So it's much like any other supernova, it's just we've lost the outer layers. And the type 1c, it's just the same thing, but doubly so. We lose the hydrogen, then we lose the helium, and then the remains of that is what detonates. So that's the type 1c. But we get sort of various types of type 2, subtypes of them in fact. So the simplest is the what's called the linear, type 2L for linear. So this one, there's a big explosion over here which we don't see because that's sort of invisible to light. Then it rises up the light curve over a number of days, up to weeks, to a peak of brightness, and then it starts to fade over time down towards obscurity once more. So that's the type 2 linear, although there isn't really any linear part of it, but that's called linear for reasonable reasons, I guess. 5 to 100 FOE for one of those. What's probably happening here is the star goes supernova and kicks off a shell of material like this with a lot of radioactive elements in, which gives this bright peak as they begin to decay and give off a lot of energy. But this shell of material is very thin and gaseous, so the light escapes from it very quickly, and that's why we see this peak and then a reasonably quick fade. Now the next type, the type 2p, so this has a light curve like this with a plateau on it, so the P is the plateau here. So again, you get the explosion, the peak, then it stays at the same brightness for quite a while and then eventually fades away. And what we think is happening here is, much like the previous one, but a much thicker envelope of material is kicked off, contains all these radioactive elements, glowing away brightly, and they get trapped within that thick envelope. So rather than the light just shooting out and coming towards us, it gets sort of scattered around and battered around between various electrons and other things, trapped within this layer for quite a while, and then eventually makes its way out. So that's why you get this sort of plateau effect of all this light being trapped inside there for a while before it can quite get out. If you're really interested, there are type 2Ns and type 2Bs and even a few other ones, but these are really only just for the supernova people who really like them. And these are the light curves that you get from various types. So you can see the type 1A there in black, more shorter lived, the type 2 linear, and the type 2 plateau, and then some of the other more obscure types. You can see they sort of all more or less follow the same thing, same sort of curve there. Then we do get another type called a hypernova, or also called a collapsar, and this is where you get a big explosion like this, shoots off a big ejection blanket, but the star or the remains is too strong and it falls back in and then gets shot out along the poles. So you get the explosion of material that goes shooting out into space, but it doesn't actually get terribly far before it falls back in and then gets sort of ejected along the poles of the star. So we get these two very bright beams. And it's a bit like a pulsar in this case. So you can see there something happening there. But one thing that hasn't really been answered is, why do the cores collapse? I've said they run out of energy, but exactly how do they run out of energy? And there's actually several ways they can do this. So the first type is a very light supernova, and this is down to something called electron capture. And this is a well-known phenomenon that we can study on Earth. Certain elements do this. So this is my model of an atom. This is the nucleus with these blue and red protons and neutrons and a green electron. And the electron is usually drawn as circling like this. This is not a very accurate quantum mechanical picture, but it will do for now. And just occasionally, this electron may get captured by the nucleus. So here it is again. It's going round and round like this. And then it can sometimes get trapped into the nucleus like this and turn one of the protons into a neutron. So that red thing turned into a blue thing and shoots off a neutrino. And so this nucleus is stealing one of the electrons that was being used. And this is what happens in a certain case. So these are called electron capture supernovas, and they occur for relatively lightweight stars for the supernova category. These are much heavier than our sun, obviously, 8 to 10 solar masses. And in this case, they've been burning for a while. They've got a degenerate core, so this would be what would be a white dwarf, except it's right in the center of the star. Oxygen, neon, and magnesium settled down there as just a degenerate core. It's not burning, it's burning helium and other things on the outer ring. But magnesium in particular is very prone to this electron capture. So magnesium can go about stealing these electrons. And because this is a degenerate core, it's the electron pressure that is holding up this core. This is what's stopping it collapsing down to a neutron star effectively. And now magnesium comes along and ruins the picture by stealing all these electrons and saying, well, I'm going to take them for my own purposes. And they are sort of a bit like pit props being knocked out and gradually knocking away the stuff that's holding up the core of the star. So eventually that fails, and the degenerate core tips over and collapses down from degeneracy down to nothing much at all, and we get this electron capture supernova. And this will give a faint type 2p plateau supernova, and you'll end up with a neutron star as the core collapses down from what was essentially a white dwarf to nothing. So that's the first type. The next one that covers quite a large range, so this is 10 to 140 solar mass stars, and these are 140 solar mass star is a huge star. Excuse me. There's quite a number of 10 solar mass and above stars. So Rigel is a 15 solar mass star, I think. But by the time you get to 140 solar mass, there's very, very, very few of those. There's like a small handful of them in our galaxy. And in this case, it's been burning for quite a while. It's gone through quite a lot of the elements, and it's burnt to iron. And we've got iron in the core, but obviously it's very compressed down there. So you've got a white dwarf, basically, of iron sitting in the center, and it's a degenerate core. And as it continues to burn, this degenerate matter will eventually tip over the 1.5 solar mass boundary between white dwarf and neutron star, and you get something the size of the Earth collapsing down to something the size of Birmingham, and it suddenly shrinks down violently as it tips over from this essentially white dwarf core down to a neutron star core and takes the rest of the star with it. So it shrinks down and the rest of the star follows it. And this is quite catastrophic. The outer layers come in at huge speed, about a third of the speed of light. The outer layers can collapse in, and then they do this bounce thing and detonate. And depending on the different sizes, you can get all sorts of types of core collapse and various neutron stars and black holes as a result. Then almost the last type, so these are very, very big stars. I said 140 solar mass stars are almost heard of, but above that you get to at least a theoretical type of supernova, which is the pair instability supernova. In this case, we have a star that is burning extremely rapidly, very, very hot as it gets towards the end of its life. And now it's burning so much that the energy coming off from all these nuclear reactions has enough energy within it that E equals mc squared. It now has enough energy that it can start to create matter. So if you have enough energy, you can make matter out of it. And at this point, it can. So it starts to make pairs of particles brand new, so typically electrons and positrons. So this energy is shooting out, and there is enough of it to create from scratch 2 new particles, an electron and positron. But this spells the demise of the star, so rather than this radiation going out and keeping the star up, so it's the radiation pressure that's actually pushing out, keeping the star from falling in. Now suddenly a lot of that radiation is disappearing into making new matter. And so when it switches into this mode, it loses suddenly this source of pressure outwards, and the star collapses in. So it switched from just making light to basically making new pairs of particles, and that's where we get this collapse. So the pair instability supernova, direct result of E equals mc squared, and burning too fast. And we think there has been one of these. This is 2006 GY, and you can see there the light curve of that plotted across there, quite a lot bigger than or brighter than quite a lot of other supernova. They're going to be extremely rare because 140 solar mass stars upwards are very, very rare. And they probably cause a type 2P and probably a gamma ray burst of the long form. So a long form gamma ray bursts, which are over 2 minutes, so not particularly long. And they probably disappear to nothing. Absolutely everything sort of vanishes in the explosion. And the final type, just to complete it, which is probably theoretical, because I don't think we know, we might know one star that is of this sort of size, above 250 solar masses. In this case, the iron core is it's basically undoing all the work it's been done. So it has a big iron core at this point, but again burning far too fiercely that the radiation begins to shatter the elements. So the gamma rays that are caused from the burning start to split up the iron into lots and lots of helium. So it's basically undoing all the work the star has been done at this point, and you also get a lot of neutrons out. So photo disintegration, it's just fries itself to death basically. There is no flash, probably a long period gamma ray burst, and a very large black hole as a result. And there's a whole spectrum of these things you can get depending on how impure you are, which is this metallicity figure up the side here. So the sun has a certain amount of impurities in it. As you go further up there, you get different types of supernova, but I wouldn't worry too much about them. Just to cover a few other things, we also have other events called like black hole collisions. So these are quite well known now that black holes do collide. We've detected them with LIGO. So these give off a huge amount of energy in their final sort of spiral, death spiral, which is coming up here. They give off, so in this spiral of the very first black hole merger, it gave off 3 solar masses worth of energy in a millisecond. So that is more energy than all the stars in the universe added together in that few milliseconds. And we've detected more than 6 now. So as LIGO gets better, we're giving off a lot. So 3 solar masses worth of energy in gravitational waves, or 5,300 FOE. So you can see it's a very intense event. We also know of supermassive black holes at the center of galaxies. They too can collide. We don't have the apparatus to detect those. We're going to need something like the spacecraft detector LISA to detect that. But if those did collide, and they're likely to collide if you get 2 galaxies merge, which we know happens, and because they're so heavy, the black holes, as they move, they tend to drag stars into their wake behind them, which slows them down, and so they would tend to come together in a reasonably short time, at least astronomically speaking. So a supermassive black hole merger would be a very, very big event, but we haven't seen one of those, and we don't have the technique to catch that in gravitational waves at the moment, although we might see something if it was in optical. Another thing that we can see is supermassive black holes just doing what they do, which is consuming stuff, and they give off a huge amount of radiation because stuff spirals into them. It gets extremely hot and gives off these huge amounts of power. So 10 to the 9 FOEs of power. But this is spread over a very long period, millions of years. So although they are extremely powerful, they're not sort of instantaneously powerful. And the other really big thing, the biggest of all, is the Big Bang. So obviously that's created everything. So the Big Bang is the biggest of all, estimated at 10 to the 25 FOEs if you're keeping score. And I thought I'd just give a very quick rundown of what happened in that. So we can roll the clock back a certain amount of time, going back to yoctoseconds or whatever they're called. I'm not too sure what they are, but 10 to the minus 41 the second is about 10 to the minus 43. It says there is the Planck interval, and that's the furthest our physics will go back at the moment. Beyond that, things don't work. So that's as far back as we can go. And then we get to this phase here where we think all the forces that we know about, gravity, strong and weak forces, and electromagnetism, were all just aspects of the same thing at this point. Something that we haven't been able to recreate on Earth. We can just about get to the electroweak scale. So the Large Hadron Collider has enough power to get to the electroweak scale, but we're not close enough to get to the grand unified scale. That needs far more energy than we can contemplate on Earth to get to. And then we get to this period in the Big Bang called inflation, which is a crazy time where the universe expands at a huge amount in such a frighteningly small time. It expands frighteningly large. So 10 to the 50 times increase. So this is how many times the universe increases in such a tiny time. We don't really have a word for it. So it sort of grows from the size of a baseball to the size of a solar system in a frighteningly small time. Far faster than the speed of light, by the way. But that's okay. Albert Einstein says you can expand space as fast as you like. You just can't send light across it. So in some sense, you can expand space as fast as you like, providing you don't tell anyone. But that inflation, which Guth came up with, solves so many useful problems in one stroke. He was trying to solve the problem of magnetic monopoles, but he turned out he solved another 3 problems at the same time. Horizon flatness and the origin of structure. So the horizon problem is the fact that if you look in both directions from Earth to the very edge of the universe at cosmic microwave background, you see about 2.73 Kelvin temperature. And to a very fine degree, it is the same temperature in both directions. But if you think about it, we're seeing light that's traveled 13.8 billion light years to get to us, to tell us it's 2.73 Kelvin. It would have to take another 13.8 billion years to get to the other side of the observable universe to tell that side I'm at 2.73 Kelvin. So this was a big worry. How does both sides of the universe know what temperature to be if they've never been in touch with each other? But inflation solves that because they were in touch before they are ripped apart by this crazy stretching of the universe. Another is the flatness problem. The universe does appear to be flat, but it's a very fine balancing act. You see the green line means that the universe is flat. If you set off in one direction, you'll go off in that direction forever. The 2 alternatives is it's sort of spherical, that if you set off in one direction, you will eventually end up where you started from, a bit like walking around the globe. And there's another form that's a bit like a saddle. But this green line is very finely poised. If you move the conditions even slightly, you end up with one or the other types of universe. So it's a bit like balancing a pencil on its point. So we can see these various geometries, and we seem to be in a geometry that is like being drawn on a flat piece of paper, which would be very unusual, but inflation sort of solves that for us. And there's also the structure problem. Why do we see structure in the universe? why isn't it just homogeneous? And that comes from the stretching out of quantum anomalies. But there you can see, if you stretch a sphere out very, very, very big, like stretching out, a sphere to the size of the Earth, it seems flat. That's where, flat earthers have a tiny bit of an argument that it does seem flat on very small scales. You have to go to very big scales to see the curvature of the Earth. And perhaps the same is true of space itself. It is curved on very, very, very large scales, but on the scales that we can see, which is basically the entire observable universe, it is approximates flat to be very fine order of magnitude. Then we get to part of the Big Bang where there's nothing happened, called the desert. Nothing goes on much there, nothing exciting. And then we get to a point where the universe has cooled down enough that we can now get quarks. So we just have a sea of quarks and gluons scattering around. And then we get to the quark-hadron transition where quarks start to come together to form protons and neutrons, the building blocks of atoms. At which point there should be a neutrino decoupling, which I'll skate over. Then we get to the lepton era, where we get protons and antiprotons, matter and antimatter cancelling each other out and then recreating each other. And then at about 3 minutes in, we get to nucleosynthesis. So this is where the universe as a whole is now approximating the internals of a star, and it's burning protons to basically hydrogen to helium, much like a star, which lasts for about 17 minutes. And we burn sort of a quarter of the hydrogen into helium at that point, and then the universe is too cool to go do anything else. That then settles down to do not very much for 380,000 years, and then we have sort of the final phase transition. This is where the universe gets cool enough that atoms form, electrons connect to the nucleus of atoms, and the universe clears at this point, and that's where we get cosmic microwave background from. Then we enter the Dark Ages, where there's nothing. There's nothing to see, really, other than obscure bits of radiation floating around. And then we get to 4 million years onwards, a few stars start to form, galaxies start to exist, and we get to see the nature of the universe as we see it now. There is another interesting point called reionization, which I'll skate over. It's a bit technical, and we get to today, where the universe has cooled down, and this is what we see. So this more or less concludes the talk. I've shot over by a little bit. If you've got any questions, please type them in the comments at this point while I do some rounding up. As I say, there's a 30-second delay, so please go ahead with any comments, and or questions, and I'll try and get to them at this point. And I'm just going to wrap up now with things to look out for. So if you want, just to summarize, if you want the Big Bang, then the Big Bang is the biggest. It created everything else. So that's kind of what you're going to have to go with if you want the very biggest of bangs. And that's happened all around us. We are indeed part of that. If you want raw sustained power, then active galactic nuclei, or quasars as they're often called in their sort of active phase, those are extremely powerful, and they can do it for millions of years potentially. So that's raw power on a large time frame. If you want to do more instantaneous things, then black hole collisions release huge amounts of energy, but they're not very exciting to see. We've quizzed a few people who do research in this, and even sort of being at an Earth's distance to two black hole mergers, you wouldn't feel very much in the sense of gravitational waves. You might think the whole universe would sort of shudder as this ripple of gravitational waves pass through, but it's so tiny, actually, even quite close to one of these mergers, you wouldn't actually feel any of the gravitational wave rippling through. So they are quite boring in that respect. There might well be a lot of other strange energies that come off from these things, but I'm not too sure about that. But certainly as gravitational waves go up, across. That's a long way away. So my money is on the, if you want the biggest bangs of all, supernovas are probably the best, the most interesting thing. And we are highly overdue, really, for one. Looking at other galaxies, they seem to happen every 50 to 100 years in other galaxies, and we haven't had a decent one in our galaxy since 1600 and something. So, that's 400 years without a supernova. We really ought to be having one fairly soon. Of course, we might have had one, and it would be the other side of the galactic centre, and we wouldn't really get to see it. But we ought to, 400 years. Come on, galaxy, give us a break. Let's see if we can see one at this point. So that's what my money's on, and the best time of year would be in the northern hemisphere about this time, so we could all see it light up. If it was Betelgeuse, we'd be able to see it in the day sky. It wouldn't ruin deep sky viewing because you can't do very much of it at the moment anyway. So this would be the great time. We could all watch it, and it would have sort of all dwindled away by October time, and we could get back to regular astronomy. So that would be the best time. So thank you very much for listening. I hope you found some of that interesting and not too theoretical. I hope so, at least. I see there Neil has come out with an excellent joke there, which you have to be a little up on your neutrino physics to really get, but very good, Neil. Definitely applaud you for that one. So another question: what kind of processes happen when material collapses into a star? So, well, there's various things. But firstly, you get a lot of heat as it collapses in towards the center. So you get a lot of stuff forced together. You get quite a lot of photo disintegration as you get a lot of radiation coming out, and you get some of these elements split up into their constituent parts again, fragmented by this high power radiation on its way. Often, say you get squashed down to a neutron star, which is what the stuff bounces off. Sometimes it will get even worse and collapse down to a black hole. But if you get one of these neutron stars, you get a lot of this neutron-rich material, and this is why supernovas give off a lot of heavy elements, because it's very easy to build heavy elements with lots of neutrons. Neutrons not being charged, unlike protons, they're very easy to interact with atomic nuclei and build up larger nuclei. So neutron-rich things are very good for building up heavy elements because they just they collide very easily. They don't get swerved away by the two positive forces getting close to each other. So that's one of those issues. So I hope that answered that, and I hope we can all get together, maybe next year perhaps, and have another talk and come up and see you up there in Cleveland and Darlington area, and see you again. But otherwise, I see my glass has come to the end, and thank you very much for listening. So I shall terminate the live stream at this point, and thank you all for your attention.